Okay, so let's have this example. For example, we have this beam loaded as shown, and we are required to draw the detailed shear and moment diagram. So first thing to do is we are to compute for the support reactions. Let's say the reaction at B, it is assumed to be upward. Let's say this is R sub B. The same with C. Let's say this is R sub C. So we have, for segment BC, we have a uniformly distributed load. If we are to compute for its single equivalent force or weight, let's say we are computing for W. W is basically equal to the area of the rectangular load. That is 120 pounds per foot. This is multiplied by the span, that is 10 feet. So cancelling foot, we have the equivalent weight, 1,200. This is 1,200 pounds. Okay, we have 1,200 pounds. And it is assumed to be acting midway between points B and C. So this is 5 feet. We may now do a summation moment at point B equal to 0, assuming clockwise moments to be positive. So we have that as 1,200 multiplied by 5 feet. Minus, we have 200 pounds, that is the concentrated load at A, that is by 4. Then minus, we have the reaction at C multiplied by 10, and this is now equal to 0. So we are computing for the reaction at point C. We have 1,200. This is multiplied by 5, minus, we have 200, this is multiplied by 4. And that is to be divided by 10. It's 520. So we have the reaction at C is equal to 520 pounds, and it is upward. That's the RC. Then for RB, we may do summation of forces vertical equal to 0, upward forces to be positive. So we have that is the reaction at point B plus the reaction at C. That is 520 pounds minus 200 minus 1,200, the downward forces, equal to 0. So we have R sub B is now equal to, that is 520 minus 200 minus 1,200. Negative 880, then transpose, that is equal to positive 880 pounds. And it is also upward. So we have R sub C is 520 pounds. We have R sub B is equal to 880 pounds. Okay, those are the support reactions. Okay, now we may start drawing our shear diagram. So for the shear diagram, we are starting on the left end, that is at A. So as you can see at point A, we have a downward force of 200 pounds. So starting from 0, we go down to a magnitude of, let's say this is negative 200. If we are to observe the span AB or segment AB, we don't have a load on the beam on segment AB. So we are to maintain this magnitude of shear. This is constant shear up to point B, a magnitude of 200 pounds. Okay, at B, we have a support reaction equal to 880. So we do the summation. So from negative 220 plus a positive reaction, 880, negative 200 plus 880 will give us a value. This will give us a value of positive, it's now positive 680 pounds. 880 minus 200 is positive 680. Okay, now we are to observe first this segment BC. Segment BC has a rectangular loading or a uniformly distributed load. The degree of that load is 0 degree. This is only for segment BC. Take note that this is for the load diagram for segment BC. We have a rectangular load. The degree of that load is 0 degree. As we go down on our diagrams, we increase the degree of the graph by 1 degree. So the degree of the shear diagram should be, it should be first degree. And as we go down on the next diagram, that is the moment diagram, Okay, the degree should be, okay, we increase it by 1 degree. The degree of the moment diagram should be second degree. Okay, again, this is only for a segment BC. So we are now performing, again, summation of forces to indicate the ordinates of the shear diagram. So this is, the last magnitude of the shear is 680. Okay, that is, we have 680 minus the weight of the uniformly distributed load, 1,200. What will be that value? We have 680 minus 1,200. Okay, that is equal to negative 520. So again, since our load diagram is 0 degree, alright, the shear diagram, the next diagram, should be first degree. So from 680, okay, we go down. So we go down to a value of negative 520 pounds. So at C, we have a reaction, upward reaction of 520. We do the summation, negative 520 plus 520. Okay, that will give us a value of 0 for equilibrium. This is our shear diagram. Okay, so next is, we are now to give the detailed moment diagram. Okay, so another key points here. Take note that, again, for the moment diagram, we have the slope. Okay, the slope of the moment diagram is equal to the magnitude of the shear. If we are to start on the free end, that is at point A. So let's say we are to place the point. This is point A, point B, then on the other end is point C. At point A, it is a free end. So it is obvious that the magnitude of moment at this point should be equal to 0. So if we are to write for our moments, this is for the moments. We have the moment at A is simply equal to 0. That is our first point. Then for the second point, that is moment at B, we have, last time if you are using the area method, the magnitude of the moment is basically equal to the area of the shear diagram. So for the moment at B, it is equal to the moment at A plus, we need the area of the shear diagram, for the segment A to B. So let us compute for the magnitude of the moment at point B. The moment at point B is equal to, what is the magnitude of the moment at A? That is 0. What is the area of the shear diagram for segment AB? For segment AB, we have a magnitude of negative 200 for shear for a length of 4, that is 4 feet. So computing for the moment at B, that is, we have negative 200 multiplied by 4 feet. So the moment at B is obviously equal to negative 800 pounds foot. This is our moment at B. Okay, so how do we write that graph? Okay, as you can see on our shear diagram, the degree of the shear diagram is 0 degree. So again, if we are to recall, if the load diagram is just for segment AB, this is only for segment AB. For segment AB, the shear diagram has a degree of 0, or that's a 0 degree. So we go down, we increase the degree by 1 degree. So the degree of the moment diagram should be, the degree of our moment diagram should be first degree. And it is a negative shear. So the value of the shear is negative 200. So again, the slope of the moment diagram is equal to, or the slope of our moment diagram is equal to the magnitude of the shear. If it is negative 200, that is a line downward to the right, okay, for a negative slope. So that is from 0, okay, we have 0 to the moment at point B. Okay, the moment at point B is equal to negative 800. Okay, so we have that as negative 800 pounds of foot. So from our moment equation, we just compute the area of the shear diagram for segment AB. That's negative 800. Okay, our next area, okay, from the shear, okay, we don't know this distance. Let's say this distance is x. So if this is 10 feet, so if this is 10 feet, segment BC is 10 feet, so the remaining distance is 10 minus x. So we can have it by ratio and proportion using similar triangles. So for segment BC, this is for segment BC. So the magnitude of the last shear at point B is 680. At C is negative 520. If this is x, this distance is 10 minus x. So we can have the value of x by ratio and proportion of similar triangles. Okay, this is, we have 680 is to x is equal to, we are using absolute value. Okay, we are not using the past negative sign. Absolute value is 520, this is divided by 10 minus x. So computing for the value of x, we have 680 is to, let's say this is alpha x. This is equal to, okay, we have 520. This is divided by, we have 10 feet, okay, minus the x. Okay, we are doing ship solve. 5667. The value of x is 667 feet. But if you are to use the actual value or the exact value in fraction, that is the same as 17 over 3 feet to avoid rounding. So we have now this distance. Okay, we have, that is x is equal to 17 over 3. Okay, 17 over 3 feet. Okay, can we now compute for that area? But at on this point, somewhere between point B and point C, we have this point wherein the magnitude of the shear is equal to 0. So we introduce a new point. Let's say that is a point D. Okay, how do we compute for the moment at point D? That is the moment wherein we have a 0, 0 shear. Okay, computing for the moment at D, okay, so we have this one. This is the moment at D. What is our previous point? Our previous point is, we have point B. That is point B, okay, plus the area of the shear diagram for the segment point B to, okay, point D. Okay, so we are to compute for that area. So we have the moment at point D. This is the moment at point D. What is the moment at point B? This is negative 800. Okay, plus, what is the area of the shear diagram, okay, for the segment B to D? That is 1/2. Its base is x. What is the value of x? That is 17 over 3 feet, or the 5.667. What is its height? So its height is 680. This is 680. So this will be the magnitude of the moment at point D. So we have that as negative 800 plus we have 1/2, or that is 0.5 of 17 over 3, or that is the 5.6667, then multiplied by its height, 680. So that is equal to 3,380 over 3 pounds-foot. So this is a positive moment. But for this case, again, if we are to recall, the degree of the shear diagram for segment BC is first degree. So the degree of the moment diagram should be second degree. So if it is a second degree curve, it is a curve. But we don't know yet if it is a curve that opens upward or a curve that opens downward. So all we have to do is, again, observe this law. Okay, the slope of the moment diagram is equal to, the slope of the moment diagram is equal to the magnitude of the shear. So all we have to do is consider the points. So what are those 2 points? That is point B and point D. So we have at point B, what is the magnitude of the shear at point B for segment BD? The magnitude of the shear for, at point B is positive. It is a positive shear. This is positive 680. Then we have the second point, that is point D. What is the magnitude of the shear at point D? That is 0. Okay? So from a positive 680, a shear of positive 680 to a shear equal to 0. Okay, how do we write our, how do we draw our curve? So what is the appearance of a line with a slope of positive, a positive slope? A line with a positive slope is a line that is drawn upward to the right. Let's say this is for point B. At point D, what is the appearance of a line with a 0 slope? Okay, for a 0 slope line, that is a horizontal line. So let's say this is point D. How do we connect those 2 points using a curve? It is a curve that opens, it should be a curve that opens downward. Using those 2 lines as your tangent lines. So we are drawing a curve that opens downward based on the slope, and our slope are the values of the shear. So we have the moment at point D. So it is a curve that opens downward. Okay, and its magnitude. The magnitude is equal to, based on our computation, that is 3,380 over 3. That is the moment at D, the location of the 0 shear. That is 3,380 over 3. That is more likely our maximum moment. In some cases, at the point of 0 shear, we can have the maximum moment. More likely, this is our maximum moment, the 3,380 over 3 pounds-foot. And then lastly, at point C, how do we compute for the moment at point C? The moment at C is, our previous point is D. That is the moment at D, plus we need the area of the shear diagram for the span point D to point C. Okay, so how do we compute for that? Okay, what is our previous moment? Okay, that is the moment at D is 3,380 over 3. Then plus, this is, what is the area of the shear diagram at point C? That is, we have 1/2. Okay, what is our base? Our base at that point, for that span, is 10 minus x. That is 10 minus, what is the value of x? The value of x is 5.667, or the exact value in fraction is 17 over 3. What is the height? The height is equal to negative 500, negative 520 pounds. So computing, Computing for the moment at point C, it is equal to, that is our last moment, the moment at D, 3,380, this is divided by 3, okay, plus 1/2, or that is 0.5 of, the base is 10 minus x. The value of x is, we have 17/3. Then its magnitude or height is negative 520. So the moment at C is equal to 0. It is expected, or one way to check our moment diagram or moments, the moment at C should be equal to 0 since that is a ruler support. But what will be the opening of the curve? Since that is, again, for segment BC, our graph for this segment should be a second degree curve, a parabola. Okay, we are to consider the values of the shear from point D to point C. So this is for segment, DC. At point D, what is the magnitude of the shear? The magnitude of the shear at point D is 0. At point C, what is the magnitude of the shear? The magnitude of the shear is negative 520. Okay, how do we write our tangent lines? So at point D, okay, the slope of a line, if the line is a zero slope, that is basically a horizontal line. Let's say this is point D. Then at C, we have a negative slope. A negative slope is a line or a tangent line that is downward to the right. This is downward to the right. So let's say this is our point C. How do we connect these 2 points using a curve? So it is a curve that opens downward. Okay? So, and using those 2 lines are tangent lines. So we have, the moment at C from D is obviously, this is a 0. That is a curve that opens downward. Also, the degree of this curve is second degree. So this is our moment diagram. And if we are to, and if it is asked, what is the maximum moment? So on this case, our maximum moment, Mmax, is equal to 3,380 pounds over 3, 3,380 over 3 pounds-foot. And it is located at the point shear is equal to 0. Okay, so this will be our solution and the shear diagram for this simple beam.